All right, let's look at some examples. So I've written down this checklist that you're going to use every time you want to use the alternating series test. So in these two series, we've already looked at them and said that they were both alternating series, right? This second one is equal to the sum from 1 to infinity of -1 to the n times n. Then we want to check to see what the limit of the terms is equal to. If it's equal to 0, then we have a hope of convergence using the alternating series test. If the limit is not equal to 0, then by the divergence test, we know that our series diverges. So let's check that here. So you can either take the limit where we keep the sign, or you could take the limit where we throw the sign out. If the limit is equal to 0, you'll see it whether or not you have the sign there, right? Because if the magnitude goes to 0, then the terms themselves have to go to 0. Okay, so to think about this, I think it's helpful to think of this as the limit as n goes to infinity of 1 over n times the limit as n goes to infinity of 0.8 to the n. We know that as n goes to infinity, 1 over n goes to 0. And this geometric sequence goes to 0 when we have a ratio less with absolute value less than 1. So we get 0 times 0 or 0. Okay, so this second checkbox is complete. All right, in this second example, when we check the limit as n goes to infinity of its terms, so we can either look at the signed or unsigned terms. I'm going to just look at the magnitude of the terms. It's equal to n, and we know that this is equal to infinity, which is not 0. So, by the divergence test, our series diverges. And so this is why I am going to suggest that you always check that the limit goes to 0 first, because if you get a positive answer, that you can keep going. It's one of the things you needed to check. But if you get a negative answer, the divergence test tells us that the series diverges. Okay, so we only have one last condition to check for this first example, which is saying that the magnitude of the terms is getting smaller with each term. Okay, there are numerous ways of checking this. So ways to check this. We could take f of x is equal to 0.8 to the x over x, and we can find the derivative and show it is negative. That one's kind of labor intensive. So we could show that bn plus 1 over bn is a ratio that has size less than 1. We could find a recurrence relation. Or we can, so that it would express bn plus 1 in terms of bn. or we can sort of compare sizes of pieces. I'll show you two of these ways. So we have 0.8 to the n plus 1 is less than 0.8 to the n. We also have that 1 over n plus 1 is less than 1 over n. So bn plus 1, which is 0.8 to the n plus 1 over n plus 1, is going to be less than 0.8 to the n over n. Okay, so that's one way of checking this checkbox. Another way is to look at the ratio of the terms. So bn plus 1 is 0.8 to the n plus 1 over n plus 1. Dividing by bn is the same thing as multiplying by 1 over bn, which is n over 0.8 to the n. We can simplify this guy, and we get 0.8 times n over n plus 1. Both of the terms in this product are less than 1, so the product is less than 1. Okay. So this is another way of checking that checkbox. All right, but overall we have that the terms of this series has alternating terms. The limit of the terms is equal to 0, and the size of the terms is always decreasing. So by the alternating series test, this series converges.